My name's Tim Poth, and I'd like to welcome you to using Wireshark as an application support engineer. We're going to take a look at a couple of PowerPoint slides here real quick. Just a quick introduction to Bentley Systems, how the priority response team, that's the group I'm a part of, uses Wireshark to support our applications. A quick introduction to the primary product we use Wireshark with, Projectwise, and then we're going to actually get into looking at some packet captures. So Bentley System is the global leader dedicated to providing architects, engineers, constructors, owner-operators with comprehensive software solutions for sustaining infrastructure. Basically, we have two core products: MicroStation, which is a CAD platform. If you've ever seen AutoCAD from Autodesk, it's basically the same thing. And Projectwise is a document management system that's claim to fame is it understands the references between engineering documents. So my group, the Priority Response Team, is a buffer between regular product support and development. We deal with everything ranging from configuration issues to crash dump analysis. Basically, we are the last stop for an issue. We primarily support two products with Wireshark: Projectwise and Select Server. Select Server is basically a licensing product. It records product usages. It's an HTTP SOAP application, nothing terribly fancy. We use Wireshark when a company has a problem with one of our applications, and normally we are not involved with the actual IT group. We're normally dealing with engineers down on the floor who are actually trying to use the product, and so they don't really know how the network was put together or how many hops they have in between them or the server, or what country the server actually lives in, or anything else. So we use Wireshark a lot of the times just to kind of figure out what's going on, where applications are sitting, how they're interacting with each other. We use Wireshark to understand how our application is behaving on their network and what kind of obstacles it's running into. Sometimes we find broken devices, sometimes it's configuration issues, and sometimes it's just flat bugs in our product. Wireshark is key to what we do because it helps us prove where and what the problem is, which allows us to move on to the next step of actually getting it fixed and getting the user back up and running. Projectwise is a client-server application. It uses a proprietary protocol on TCP port 5800. It has nothing to do with VNC. A lot of people see that and they think VNC. No, nothing similar. We use a mechanism called Delta File Transfer to actually speed up file transfers. Basically, if you have 90% of a file, we don't want to make you download the entire 100% all over again. We just send you the 10% that you're missing and maybe a little metadata to put it into context. Whenever we do a file transfer, we actually spin up a new TCP session. That'll become important a little bit later on. And our application supports application level gateway and routing infrastructure. So basically you would send traffic to a server that would forward it on to another server kind of independent of your network architecture. The roles that our servers can be is an integration server. This is kind of where the data lives. A gateway server, it does gateway functions. A caching server, which does file transfer stuff, and a web server that does web stuff. We do have a web server component. It is an ASPX page based application, uses ActiveX for a file transfer. A data source is something that will come up a little bit in the captures today, and it is basically a collection of folders and metadata hosted on a server. One server can have multiple data sources, each data source can have many files, etc. So we're through all the boring stuff and into the actual packet capture. So the first capture we're going to look at here today is a odd frame sizes in a capture. I was looking into a file upload issue for a user, and I was trying to follow what was going on to make sure we weren't screwing up a buffer or something, and I started to look at exactly how much data was in each of the frames, and I got kind of alarmed. So we'll go ahead and jump out to that capture. And this is a capture that I made from my client machine. And as you can see, everything kind of starts out pretty normal here. I have a length column added to kind of make it easier than trying to read through the sequence numbers and the acknowledgement numbers and stuff. And you can see everything's going pretty normal, and we get down here and we've got a 2900 byte packet, then we've got a 5800 byte packet, and then we've got an 11,000 byte packet and a 23,000 byte packet. If we actually go ahead and sort by length and go up to the top here, you can see the largest packet that we have going across here is 35080. Well, that's That's huge. That's incredible. How are we possibly sending that much data on a network at any one time? The largest frames you can have, even with jumbo frames, are in the 9K range. So how the devil did we get up to 35K? So I went ahead and I went and did a capture on the server, and this is the exact same session, just from the server's perspective. As you can see, things from this side look a lot more normal. We've got, our 40 byte ACKs going back, but then we have full 1500 byte frames and nothing larger than that, and everything looks nice and consistent at that point. So what the devil's going on? It's how are we seeing packets of this size going across our network from the client, but the server has a completely different perspective on the world? Well, what I actually came to find out is if you take a look at your network card, there's different offloading options. Most of you are probably already familiar with the TCP checksum offloading, where rather than the operating system having to calculate a checksum on every packet, we let the network card handle that because the network card's nice and fast at this point, and why should the operating system be bothered? What we find out is they've actually given some more offloading work to the network card, and it's a large send offload. Basically what this allows an application to do is, rather than having to send the data to the operating system and have the operating system chop it up to send over the network, the client application can actually stream the data directly to the network card, and the network card gets to figure out how best to chop the stuff up and send it across. And so that's exactly what we're seeing in the client capture situation. We have this offload option turned on, and so the application is just sending these chunks of data across, and our application tends to chunk data up into 32K chunks. The 35K chunk there is kind of an anomaly, but that's a different issue entirely. The large send offload also goes by a couple of other names. It's known by segment offloading, TCP segment offloading, TCP multi-data transmit, and TCP large send. And depending on your operating system, your NIC drivers, these are the common terms you may see. You may find that you've got some really bizarre wording in there, but that's basically what we're looking at. We'll go ahead and close up a couple of windows here, and we'll move on to the next issue. So this is a DNS issue we ran into. The user is trying to pull back a list of domain controllers for our application, and it's failing. But when they do individual requests, it does work. So we've got a couple of different servers in play here. We've got the Projectwise server, which is essentially our client in this case. We have a domain controller that it is connecting to for DNS data, and the domain controller list it's actually requesting is from domain B, and there's actually 3 domain controllers across a WAN link that actually contain the data for that domain. So we'll start off with the failed case here, and I'm going to set focus down here just so we can see the top a little bit easier. We've got a couple of different machines communicating here, and it can actually be kind of hard to follow the bouncing ball and to keep straight which one you're looking at when just they all kind of colorize the same. So one of the things I like to do here is actually break out one of the machines into a different color, and in this particular case I'm going to pick on the client because it's a little bit easier. There's 2 ways of doing this. You can always go in here and create a custom coloring rule based on IP address or whatever unique data you want. One of my favorite features is to actually come down here and do a colorized conversation, and we can do it on IP, and we can just go ahead and quickly select a color. It doesn't make any changes to the coloring rule, it's just kind of there for this particular session, and it lets us kind of break things up very easily. So it makes it a little bit easier to read. We can now see that the client is sending a request off to its local server. The local domain controller is sending a request off to the next domain, and then we're getting a response back. So if we look at the actual request here that's going across, we can see that it is an Active Directory request, and we're actually trying to pull back a service record for some LDAP data. If you're not familiar with this construct here, don't worry about it, don't get hung up. It's an Active Directory way of, or it's an Active Directory construct for using DNS. There's nothing terribly special about it. It's just kind of the way they do it. So the client sends off a request, the client's domain sends it off to the remote domain, and we do get a response back. Now the response back is no such name, which from an application perspective you may say is a bad thing, but from a DNS perspective, DNS is working. It is doing what it's supposed to do. We asked a question and we did get a definitive answer. The answer just was that there was no data that you were looking for. And so our server, the local domain server, actually sends it back to the client and the request is complete. If we look down here at the next line, we have the client making another request, and it's going to a slightly different URL, but still off an Active Directory land. We're still looking for a service location record. And we have the local domain controller sending this off to the remote domain. But if you look at the next packet here, we can see that we have another request for the client. If you look at the delta, I'm a really big fan of having a delta column up because it helps break things out a little bit. You can see that the client waited about 2 seconds and got a little bit fed up and asked the question again. And about 2 seconds later, our local domain controller decided, well, I haven't gotten an answer, it's been 4 seconds, let me try another server. So we go ahead and we send a request off to a second server. The client, very impatient, only 2 seconds, it wants to know where its answer is and it asks again. Our server, a little bit more patient, waits 4 seconds, and then it picks yet another domain controller to ask this question of. Client asks the question again. The client was patient this time, waited a whole 4 seconds to ask the question, but is still asking the question again. And our DNS server just gives up at this point and tells the client that there's no answer back. So what happened here? I mean, obviously we were able to get a response back from the server up here. We got a response back, no such name. But when we asked what appears to be a smaller question, we never hear back from the server. Not only do we not hear back from the one server, we don't hear back from 3 different servers. And we waited a whole 4 seconds each time, and we didn't see nearly that much time transpire up above. So one of the things I like to do when I have questions I can't answer is kind of pull the packets apart and try to look at them. So if we kind of pull apart the client request, and it doesn't really matter which one you pick on, they all kind of look the same. That's not a request, that's a response. This is a request. So we can see this is a pretty straightforward DNS request. It looks pretty standard. It looks like, you know, every DNS request I've ever seen. If we actually take a look though at the request that the local domain sent on to the remote domain, something might grab you here. There's something a little bit extra in here, and it's this additional records. And if we actually go and expand into this, we can see that it's some optional data, and it's some eDNS0 optional data. And one of our hints here is that it's pointing to a UDP payload size of 4,000. If you actually go and look up eDNS0, you'll actually find out that it is an extension that was written for DNS, because back when DNS was originally envisioned and created, the requests were limited to 512 bytes. Well, this was great for the internet way back in the old days, but really 512 bytes is pretty limiting in the modern world. You have companies with huge lists of domain servers, you have redundant servers strung out all across the world for websites. 512 bytes goes really quickly when you're talking about DNS data, especially when you're talking about longer URLs. So that's what eDNS0 was written for. If we come over here and take a look at an example of eDNS, this is a standard query that I set up in a test domain. We're just doing a standard A lookup, and this is looking up all the domain controllers for this particular domain. And you can see we have the request here, and then we have 2 kind of funny looking packets, but they're actually, if you note here, they're reassembled in packet 4. They're actually a stream of data coming back from my DNS server. And if we look down here, this is where the response actually wraps up. And if we look here at the answer, all of these servers wound up coming back in this response. So we're using eDNS0, and we have well beyond our 512 byte limit. We actually have 2 full 1500 byte packets, and then just kind of the trail in this very last packet where Wireshark reassembles it all for us. So all this being said, back to the original problem, what's actually going on for the user? Well, as it turns out, they actually had a firewall in place that did not understand the existence of eDNS0. It didn't understand that DNS requests could possibly be larger than 512 bytes. And so the requests were making it through perfectly fine, but when the response came back with those larger packets as a DNS response, the firewall said, no, 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 no. You're way bigger than you're supposed to be. Something funny's going on here. I'm going to put a stop to you. The user wound up deciding to turn off eDNS0 on both sides of the firewall, both domains. Don't know why they chose that rather than, upgrading to a modern firewall that actually understands modern things, but that was the user's solution in this case. If you're interested in learning more about eDNS0, it's actually RFC 2671. RFCs are interesting reading, but it's a good time, and I definitely encourage it. So on to the next issue, and this is a database performance issue. We have a user complaining about application slowness, and the logs show delays getting data back from an Oracle server. Now, when I hear application slowness from the database, I don't immediately think let's use Wireshark. But in this particular case, this database connection was coming across a WAN link. Don't know why, but the user had their integration server in data center A and their Oracle server in data center B, and they had this link in between, and so we immediately got very concerned. Database traffic can be very chatty, and it can suck up a lot of bandwidth and can be very latency sensitive, so maybe that is related to the issue. So we'll go ahead and bring that up here. And we'll go ahead and start off with a log snippet. So this is the actual SQL statement that was causing us trouble, this whole big mess in here. I'm not a SQL guy, I can't tell you if this is good, bad, or indifferent, just this is the query that we were doing at the time. If we come down here to the very bottom of the log, we can see that as far as the application was concerned, it took 174 seconds for us to get a response back. So that's definitely a long time for a client to sit around and wait for an answer coming back from a database. So there's something going on here. So this is the packet capture, and we had this running at the time when the user reproduced the slowness. And you can see we've got 2,800 packets in here, and it's just kind of a mess. So how do we go about figuring out where the data is that we're looking for? One of my favorite features in Wireshark is the ability to do a find. So what we'll do is we'll go ahead and copy a bit of the SQL statement we're looking for. We'll go and do a Control F, and we can actually go ahead and specify a string. And you've got a couple of different choices here. You can do the packet list. This is any data that would show up in the top frame here. Packet detail. This would be any data that's going to show up in the middle frame. And packet bytes. This actually combs through the raw bits and bytes down here. And as you can see, just the random packet I happen to be on, the SQL stuff's going to be in plain text. So you can kind of read that this is a select statement in here, and we're searching for some different things. So that's going to be what we're going to do. We're going to just search for this in the packet bytes. Now, when I first click the find, it kind of doesn't seem like anything happened. And unless you have a real sharp eye, you might not notice this message down here. Let me get that to come back. No packets containing this string could be found. Well, that's kind of frustrating, but the reason I showed that to you is if I go ahead and strip the from off, suddenly I can find the packet we're looking for. And if we actually look at the bytes down here, you can start to see why. We have in the actual bytes from the @ symbol and then the rest of the string that we had. Well, where did the @ symbol come from? Unfortunately, that came in from the ODBC driver. Again, I'm not a database guy, so I can't explain why the ODBC driver decided that it would be fun to put that in there. But the ODBC driver decided that that belonged in there for the way it and the way Oracle wanted to parse this query. And so when we did the search, it kind of threw us off. When you're doing a search, it's great to have a nice specific thing you're looking for, but if you're not finding what you want, you're going to have to start generalizing it, and you're going to have to start paring it down and seeing what else you can find, because sometimes you run into situations like this where an application shoves something in there. So we've got where our SQL statement was. So what can we learn from the capture here? Well, if we look down, This is coming, the SQL statement, or the SQL request, the select statement is going to come from our client. So we can go out on a limb and make an assumption that this 77 machine's our client. And if we look at the next frame, it might not be obvious, but this actually is the parameter data that we're passing along. If we reference back to the log, you can see we've got parameters here. The same parameters that show up down here. It's not intuitive, but so we've got parameter data. The very next packet we have here is an acknowledgement, and this looks to be coming back from our SQL server, or our Oracle server. So this is a good thing. We can see that our delta on here is 1 millisecond. So at a TCP level, we can feel reasonably confident that the Oracle server did get our request. If we look at the next frame here, we've got a little bit of data coming back. You can see this is a full 1500 byte packet. And again, it might not be terribly obvious, but as you actually scroll down through here, this is a list of columns that are actually coming back for our query. So these are the columns for the data that we're requesting, and we can actually go and line these up with the SQL statement if we wanted to, but don't have to do that. There are columns. So this tells us something very important right off the bat. Since we finished sending our parameterized query across, we got an acknowledgement in 1 millisecond, and then we actually got a column list back in about 26 milliseconds. So our request clearly reached the database in good time, and we're starting to get some feedback back from the server. So we get a little bit more data back from the server. Our client goes ahead and acknowledges it. It's what you're supposed to do. And then we can see our delta column here. There's the delay that showed up in our logs. We've got this 174-second delay. So is this a networking issue? At this point, we can feel pretty confident in saying, no, the request made it to the Oracle server, and the Oracle server did give us an initial response back of the columns, but it took it a long time to get the data together for us. So this probably isn't a network issue. Their WAN length, however they're using it, is probably perfectly fine. The issue is really back on the Oracle server end. Well, I certainly didn't bring this capture up just to tell you that the problem was back on the Oracle server end. So if we actually scroll around in here and look at some other things, there's actually something else that we can learn that's really interesting. If you start to take a look at how the data comes back from the server, you can see that we've got a nice 1500 byte frame when the data initially starts coming back, but then we've got a 223 byte frame coming back. And so our client goes ahead and acknowledges it, and then we get another full 1500 byte frame, and then we get a 591 byte frame. And we acknowledge that, and then we get a 265 byte frame, and we acknowledge that, and then we get 1500 and then 312. Well, this all seems terribly inefficient. If we are sending this data back, why is it all broken up? I mean, why can't we just send a whole bunch of 1500 byte packets across? Why do we send a full-size packet and then a little packet and a little packet and a full-size packet and a little packet and a full and a little? And this seems excessively chatty. I mean, why can't we just stream this data back? Well, it actually turns out that Oracle has some different parameters that you can tune on how it sends data across the network, particularly how its buffers pull data out of the database and packetize it to be sent. And in this particular case, the settings were tweaked in such a way that Oracle was only going to return one row at a time to the user. So depending on how much data was in that particular row that was coming back, depending on exactly how many packets it got broken up to. But this is very inefficient. One step further, if we take a look at what time this happened, the user was actually doing this test just before 5 o'clock in the morning. How busy is your average network at 5 o'clock in the morning? You might have some backup jobs and stuff finishing up from the night, but generally speaking, you don't have a lot of people on doing stuff. If you come to the middle of the day, you're going to have a lot of extra traffic flowing around. Now, the individual latencies on these different packets really isn't all that bad. The problem for the user was this big delay starting it. Getting the data back to him only took a few hundred milliseconds. It really wasn't that bad. But we have all of these extra packets in here, and when you're talking about the middle of the day production hours, this is just going to amplify, and it does actually start to create its own problem, and it does actually start to create different issues on your WAN link. So in this case, the user really had two problems. One, they didn't have their Oracle parameters tuned quite right, and unfortunately I can't tell you exactly what they are because I'm not a database guy. But the other problem was how long their server was taking to generate the response and send it back to us. The actual query itself had to do with the disks in the server and how the data was stretched across the disks. They wound up reordering that a little bit and it improved things. And then they did actually see some improvement by making some changes to Oracle to better utilize the available bandwidth. So, next issue we're going to take a look at here is actually a select server issue, and this is where a user is trying to post some data back to Bentley and it's failing for them. So this capture is already filtered down to TCP port 80, but there's still a lot of stuff going on the screen here. We can see that we've got 128 packets down here. The conversation stretches well beyond what we can see, and there's a lot of noise in here. It's not easily readable. So one of the things I like to do is when you start off with something like this is to try to filter it down a little bit. Sometimes it helps, sometimes it doesn't, but a lot of times it can make the problem a lot more apparent. So right off the bat, the problem almost kind of jumps out to us at this point. We're doing a request and we seem to be getting these 503 service unavailables back. If we look at the requests here, it looks like the client's going to be this 10 dot address, and it looks like the server here at Bentley is going to be this 64 address, and it kind of looks like the service unavailables coming back from Bentley. So that's kind of interesting. Nobody else is really having this problem. We don't have other users reporting this, so it seems to be this one site, but it looks like the response is coming back from Bentley. So what do we do to figure out where this is actually coming from? How do we figure out who's really at fault here? Well, at this point we do kind of want to go back to the prior view, and we do kind of want to dig into the individual bits and bytes of the packet. So what I'm going to do is follow stream on one of these requests and try to get the whole view. We'll actually switch back to that other window in a moment. So as we start to take a look at the way things are laid out here, we can see that we've got our SYN, SYNAC, ACK three-way handshake, and we have an acknowledgement going back to the server, or we have the beginning of a post going back to a server. And we can see that this is the actual beginning of the post request here. And we're getting a response back from the server. Okay, got the first part of your request, go ahead and send me a little bit more. And the client goes ahead and finishes the request at that point. And that's when we see the 503 pop in. So our servers are at least initially responding because we are getting this continue message. So the client's not being rejected right offhand. We are communicating at some level. But we still got this 503 down here. If we go and take a look at the actual text of the stream, this is where the answer really starts to come together for us. The title, if you look at this content here, it's an HTML page, and if we were to actually scrape this up and go and put it in a notepad document on our desktop, we could actually bring this up in Internet Explorer. But it's pretty simple, so we can go ahead and read through it here. We can see that the title of the page here is Application Blocked. Well, it's kind of unlikely that Bentley would block the application that the users are using for our licensing. I mean, we got a pretty good handle on what we wrote to do that, so why would we block it? If we come down here a little bit more, access to the application you were trying to use has been blocked in accordance with company policy. Again, Bentley's not really going to block communication to its licensing server for our licensing application. Contact your system administrator if you believe this is an error. So what's really telling, though, is we have some user information in here. Well, if you look up at this post request, nowhere in here do we convey any user information. There's nothing that really identifies this particular site. So when we come down here and look, I mean, how would Bentley server possibly know the user information? The next point of interest here is the application is referenced as SOAP. What we wound up doing is talking to the user about this error message, and we come to find out that they actually had a proxy server in place. I don't know the exact brand of the proxy server, but it turned out that their proxy server had some very specific rules in place about SOAP data. And because of these rules, they were actually blocking our application, and they actually needed to go in and make a change to allow that. So it kind of started out as looking like Bentley was refusing the connection, but as we started to pull it apart and dig in a little bit, it was actually somebody in between who was responding on Bentley's behalf. I guess they were trying to be helpful. One interesting note while we still have the packet list up here is if you note these FINACs, the client, after it receives the unavailable from the server, goes and tries to shut down the communication. Well, if everything was really communicating the way it appeared to be up above, we should have gotten a FINAC back. But the client's FINAC actually goes unanswered, and the client actually goes and tries a couple of times before it just gives up and kills the connection and hopes the server got the message. Again, it implies somebody's in the middle of the communication doing something a little abnormal. If a server tells you it's unavailable, it's probably coherent enough to acknowledge your FINAC that's coming in. When a proxy device or a firewall shuts down the communication, they tend to be a little bit ruder about things. So issue number 5. We have a user connecting to a Projectwise cluster using a index server, what we term as a tail server, using a Projectwise client on that indexing server. When they do that, they get a socket error. And what's really odd is that all the other clients on the rest of their network are working perfectly fine. They've got users out in the field actually using the product, and they don't have a problem. It's just when they try to come in from this tail server to the cluster. There are 2 integration servers in this cluster, often referred to as a head, and it is a network load balancer cluster. So we went ahead and we created a capture on the integration server, the head server, and the index server, the tail server. And in order to simplify our lives, we went ahead and failed traffic over to one of the 2 head servers. Now, this isn't always possible. Depending on the load of the network, you may find that this is a really bad idea in some environments. But in this particular case, the user was able to do this for us, and so it made our lives significantly simpler. So we have the head server's IP address is 151. The tail server is 154. And the actual cluster IP address for this head server is 247. And this is a network diagram for the situation. So we'll go ahead and take a look at the captures. And we'll go ahead and start out on a tail because it's a little bit more interesting to start on the tail. So we've got the tail server here, 154, communicating to the clustered IP address, the 247. And we have a SYN, SYNAC, ACK. Great. Everything looks really good at this point. Well, then we get a SYNAC that comes back, and this SYNAC's coming back from 151. The SYNAC's coming back from the integration server itself. Well, that's kind of odd, and then the client goes ahead and resets it. Well, why does the client reset it? The client resets the SYNAC because it is not in response to a SYN that the client sent. So as far as the client's concerned, it wasn't actually talking to that box. It was talking to the 247 box. So it has no idea why the 151 box is sending it a SYNAC. So it goes ahead and resets it. And then we get another SYNAC, and we get another SYNAC, and we just keep resetting them. We do have the client sending some data to the cluster, but we never actually get any data responses back from the cluster. We're sending 42 bytes of data, so it's a 40-byte IP packet and then 2 bytes of data, part of the handshake process, and we get an acknowledgement back from the load balancer, but we never actually get any data back. We're just getting these acknowledgements. So what's going on here? If we go ahead and flip over to the head server, we get a SYNAC that comes in, but if you notice the IP address, it's not coming from the cluster, it's actually coming from the client. So in this case, the client sent the request to the cluster, and on the integration server side, the head side, we see the request coming directly from the client. If we look at the SYNAC, of course the server is going to SYNAC back to the client because that's where the request came from, and then the client goes ahead and resets us. And then we get another request that comes in from the client. So what's going on? Why are we all confused here? If we go and take a look at this request, and if we take a look at the MAC addresses here, we can see that the integration server, the head server, is a VMware machine. It's an O3 machine. And the request is coming from this IWIL adapter. If we flip back over, we can see that the 54 address, the client, the tail in this case, is a VMware machine, and it's sending a request to this IETF box. Well, this is actually a well-known MAC address, and it's actually used for clustering purposes. So this isn't really a hardware vendor like you traditionally see, but this is a clustered type of virtual MAC address. If we come and look at some of the responses, though, that we get back from the cluster, we can see that it's coming from the IWIL. So our client's sending it off to the cluster, which appears to be this IWIL device. The IWIL device is sending the request on to our integration server, but it's sending the request on unchanged. Clearly the MAC address changed because it's resending the request, but it's still passing around the client, the tail server's original IP address. When our integration server goes to respond, because the tail server and the head server are actually on the same physical segment, they're actually plugged into the same VMware switch, they know each other's MAC address. And so when the integration server responds back, it responds back directly to the client. It doesn't send it back through the cluster. When the other end users out on the production floor actually come in and make a connection, they're on a different VLAN, so they're in a different address range. So when these requests come into the integration server has to redirect them back through the hardware load balancer to make it back to the client. So there's no other way for it to make a direct connection, and so the clients don't see this problem. But because these two boxes live on the same network, the responses are coming back out of bound, and they're actually confusing the situation. So in this particular case, what the user did to resolve the issue is they actually enabled NAT on the network load balancer, and this caused the traffic going to the integration server to look like it was coming from the load balancer, and so the request always went back the right direction, and everything worked quite well at that point. So moving on to the next thing, we have a file download issue. So the user is trying to download this pump house file from Projectwise, and it's hanging for a few moments, and then it fails with an error. And the error doesn't really make sense, and there's nothing really in the application logs that tells us what's going on. So if we go ahead and look at this capture here, right off the bat you can see that there's not just Projectwise traffic in this capture. Right off the bat we've got some yellow SMB in here. So what I'm going to do is try to simplify it down. We've got 2200 packets in this, so I'm going to see what I can parse this down to. So because our application runs on port 5800, I'm going to filter on tcp.port equals 5800. And you can see that we've roughly halved our packet count here, so that's definitely a good place to start. And how do we go about finding where our transfer is? Well, if we go ahead and use our good old search again, we'll go ahead and do a string and packet bytes, and we'll go ahead and focus on that file name. We can actually see that shows up in one of the requests. And Projectwise using a separate TCP stream for file transfers actually really works out well in our favor in this case. So what we can do is we can go ahead and follow stream on that. This particular part really isn't useful, but all of this data here is just that file transfer. Now we're down to just 850 packets that we have to deal with from the original 2200. So we've taken our problem and we've cut it down a little bit. Now we could go and scroll through this and look at all the different packets in between, but we know that we get to the end of the file transfer according to the progress bar, and things kind of hang for a few moments and then they error out. So we can go out on a limb and we can say, well, the problem is probably down towards the bottom of our capture. So if we go ahead and shoot down here to the bottom, you can see that we're getting nice 1300 byte packets back, and we get a little bit of a smaller packet back, and then we go ahead and we send some acknowledgments across. So this actually makes it look like the communications have probably wrapped up and that we're finished downloading the file. We have our nice 2-second lag here, so this kind of goes back to what the user was seeing, where it pauses for a moment before giving an error, and then we go ahead and close up the session. So what's going on here? A lot of times when I see a gap in time here and I see that there are a number of packets in between, I want to know what happened. Sometimes it's interesting, sometimes it's not. So what we'll do is we'll go ahead and clear our filter here and kind of see what's in between. And what we see here is we've got large packets going back and forth, and if we actually click on one of these, we can see that the port is port 445 that this is going to. Now you might not know that right offhand, but this is actually for SMB traffic. And if we scroll down and look through here a little bit, you can actually see that there are some SMB command frames going back and forth. So that's kind of interesting. Well, what's this SMB stuff doing during this gap in time? Now, this is kind of noisy looking at all these individual packets, and they might be important and they might not be. So what I'm going to do is I'm going to go ahead and change my filter here a little bit, and I'm going to use my original capture, and I'm going to add a OR SMB onto it, and we can kind of get an idea of what's going on. So we have our Projectwise traffic here, and then we have where our SMB traffic picks up. If I scroll over and look a little bit, you might recognize that this is the file that we were trying to download. So that's kind of interesting. So we're downloading this file, and it looks like we might be downloading this file off to an SMB share. So how could that play into our error message? If you notice, we have this DFT temp on the end of it. And this actually goes back to how we do our DFT processing. We have the original file, a .dgn, and we make a copy of that DFT temp, and we go ahead and we apply the deltas to it. And the reason for that is if something bad happens, all we do is trash the temp file. We don't actually trash the original data that you have. So if you go and have to retry the communication again, we have something to work from. We haven't pushed you all the way back to square zero. So you can see we're querying and we're getting some information on this DFT temp. And as we come down through here, you see that we go ahead and do a delete request for the original file. Well, once we have that temp file all built up, we need to delete the original and then move that temp file into its place. So this is pretty normal, and if we look down a few frames, we have a delete response. So what happened in the delete request? Well, if we look at the SMB header here, we can see that we got a success back. So that's great. We asked for a delete, we got a delete. Just what we needed. So if we go ahead and look at the next frame, we're going to do a rename, and we're going to rename the temp file to the DGN. And our very next response is error, name collision. Well, how could there possibly be a name collision if we deleted the file that we were trying to rename it to? So if we go ahead and drift down a little bit farther, we can see that we go ahead and we try to do a query for that file again, and that's when the server starts to tell us what's going on, and the status we get back for that query is delete pending. So we asked for that file to be deleted, and the server said sure, it's deleted, not a problem. But actually that wasn't entirely the whole truth. The file's actually pending deletion, so you might have to wait a few moments. So our application goes ahead and tries a couple of times, and we just keep getting told that the file still hasn't been deleted, and so we give up and we move on and we return an error back to the user. So not really something wrong with a network per se, but communicating across the network, we're getting lied to from the remote server, and something's going on that's causing it to be a little bit slow to process this delete request. Now the user went ahead and resolved this without letting us know precisely what they did, but we're pretty sure that they had something running on the server such as antivirus or an indexing service that went ahead and put its hooks into the file when we went and did the query information on it. And that's what an antivirus server is supposed to do, right? It's supposed to go ahead and intercept requests for a file and make sure it's clean before it lets you do something that hurts you. And in this particular case, it looks like, whatever it was didn't get out of the way fast enough, and so it caused us to wind up timing out on our operation. So while we're on the case of SMB, we're going to look at another example. This actually doesn't have anything to do with a Bentley product, but it was something interesting that came up that I enjoyed. So we have a small office that just put in a new file server. It's a 2008 R2 box, and they're setting up a old scanner to scan to this server. We went ahead and we created a capture on the server of a scan attempt failing, and we did a capture on my laptop showing that the network share really could be accessed. So we'll go ahead and start out. This is the error message we were getting back. Nothing terribly helpful. Thanks, but didn't do much for me. So we'll go ahead and start off with the scanner request. When we have a good request and a bad request, it can sometimes be difficult to figure out where things are going wrong. So it's usually helpful to start on the bad request because it's usually shorter. There's usually some sort of error message that you can key on, and then you can figure out how the good request differed. So we've got a whole bunch of different packets in here, and again, I want to just kind of simplify this and make it a little bit easier to read. So I'm going to go ahead and filter on SMB. Now you see there were some SMB2 packets in there. It certainly could have been SMB2 that we were dealing with. When I filtered on SMB, and if I didn't find anything, I might have failed back over to filter on SMB2. But in this particular case, things kind of pop right out for us. We can see that we have a user request going through and the user is scanning, so that's a pretty good indication we're dealing with the scanner. We can see that the path that we're accessing, and we can see that we get an access denied back. And we go ahead and we try this twice, and both times we get an access denied. So what's going on in the good request? So again, we can go ahead and filter down on SMB. And it doesn't do too much in this particular case. We still got a lot of traffic in here. If we go ahead and do a find, and if you look, the path we were accessing is com-ad/main. So we can actually go ahead and do a search for that same thing. We will try to do a find in the right window. Okay. So we go ahead and do we found it here, and we've got two different instances where it comes up. And in this particular instance, it is a get DFS referral. This is a distributed file system referral. Well, that's not the same request we were doing back here, so we're going to go ahead and ignore that. If we look down a little bit, we can see we're doing a tree connect and request. Well, that is the exact same thing we're doing back in the failed state. So this is a really good point to key in on. So we're doing the request here, and obviously in the good client's case, it does succeed. So why does the one succeed and the other one fail? Well, I'm going to go ahead and make these columns a little bit bigger and move my windows around a little bit. Whenever you're dealing with a request that doesn't really make too much sense, you kind of have to pull it apart, and you kind of have to figure out where things differ. And so what I'm going to do is I'm going to go ahead and just drill down through the SMB here and try to see what's going on. And if you're looking at things, you might notice that our flag columns differ a little bit. And I'm going to go ahead and expand flag 2 because that's a little bit more interesting here. And you can see that there's a couple of things different right off the bat. Unicode strings are ASCII and Unicode strings are Unicode. Well, that's interesting, but that doesn't sound terribly exciting. Error codes are NT error codes are DOS error codes. Again, I'm not excited. Well, if we come down, we start to see some much more interesting things further down. Extended security negotiation is on in this particular case. Security signatures is on, and extended attributes is turned on. And all of those are actually missing in the request from the scanner. So as we start to search around on these a little bit, we actually just went out to Google and started to search to learn a little bit about these different flags. And what we actually came to learn is Microsoft made a lot of changes in Server 2008 R2, particularly on the domain controller side, particularly when it came to security. And in this particular case, there is a group policy setting, Microsoft Network Server digitally signed communication always was set to on for the default domain controller policy. And our poor little scanner, being from the old days, didn't understand digital signatures for communication, for SMB communication, and didn't know how to participate in this with the server, and the server took a very hard line and said, well, if you don't communicate with digital signatures, then I don't really want to talk to you all that much. And so our poor little scanner was kind of left all alone. Our initial thought was, well, there's got to be a firmware update for this thing, right? Unfortunately, this is a bit of an older unit, and there were no firmware updates. So in this particular case, we wound up relaxing the security policy a little bit and setting the digitally signed communications to negotiate. So if a client was willing to do it, great, but we weren't going to force them so that the scanner would continue to work. We came to decide that was a little bit cheaper option than going out and buying a whole new scanning unit for them. So that actually brings us to our last capture of the day. And this is a random connection issue. A user at one site, users at one site randomly cannot connect back to an integration server across a WAN link. Now, right off the bat, this network diagram should scare you. Why does this particular server have 4 different routes across a WAN back to the integration server? That's kind of scary, and we'll see how this network diagram came to be here in a moment. So we'll go ahead and open up this capture and go ahead and resize things a little bit. And right off the bat, you'll see these black and green packets. These are ICMP packets, and they're redirects. Well, that's a little odd, but we don't really know what it means at this point. So we're going to go ahead and put it on the back burner. We're going to go ahead and look at this very first TCP connection here, and everything looks pretty good. We've got a SYN, SYNAC, ACK, and as we kind of drift down through here, everything looks like it's communicating to me. So what can we do to figure out what's going on? Now, granted, there's only 600 packets in this particular capture, but originally this was much larger. It's kind of been pared down for this example. So what kind of things can we do to kind of narrow down on where the problem is? Well, there's a really useful filter, and it's TCP Analysis .flags. And what this will do is it'll go ahead and look for alerts that have been flagged in the TCP communication. And we've got red and black here, so that's kind of not a good thing. And we've got some previous segments, previous unseen segments. We've got some duplicate ACKs. Well, that's a little bit interesting. So if we go ahead and select one of those and clear our filter, what do we have going on? Well, we see some more ICMP packets in here, and we see the beginning of a TCP session. And we have a SYN, SYNAC, ACK, and then we've got these segments, and it's spaced out, and you might not notice it right away, but we actually have 2 different TCP threads going on here. We have 6340 and we have 6334. So it can be kind of hard to follow what's going on. So what we're going to do is go ahead and select one of these previous unseen segments and go ahead and do a follow the stream. We don't really care about this window. We're trying to get a feel for what's going on, and this kind of makes the problem a little bit easier to see. It kind of condenses the communication for this particular session. And here we have a SYN, SYNAC, ACK. We've got a push ACK, so we're sending a little bit data. We get an acknowledgement, but then we get a SYNAC back. It's labeled as a ACK to an unseen segment, and that's based on how Wireshark analyzes the sequence number and the acknowledgement number. But this kind of goes on for a little bit, and then the server eventually resets us. So what's going on here? What can we tell? Why is this so different than the communication that we saw earlier? Well, when we have something that doesn't really make sense, we kind of have to pull it apart and start to look and try to figure out what's going on here, who's talking to who. So we have our client sending the original SYN out, and it's going to a NetScreen device if we take a look at the MAC addresses here. And when we look at the SYNAC that comes back, we're getting the SYNAC back from a Riverbed device. Now, is this a problem? Not offhand. It is a little odd, and it does make things hard to follow, but this is technically allowed. You can have packets taking asynchronous routes, and you can have them doing odd things on you. So right offhand, this is not necessarily a bad thing. If we go ahead and look at the next acknowledgement we send it back to the NetScreen. We send a little bit of data to the NetScreen, and we get some data back from the Riverbed. So up to this point, things have been nice and consistent. Odd, but not a problem. Things get strange when we get this SYNAC back. In this case, we're getting it back from an ADTRAN device. Well, we weren't talking to an ADTRAN device at any point, so why are we getting a SYNAC back that is part of the same TCP stream, but it's from a completely different device? So we go ahead and we know it's part of the same TCP stream, so we go ahead and we send a acknowledgement back, and we get another SYNAC, and we acknowledge, and another SYNAC, and acknowledge, and all the time we're sending to the NetScreen, and we're getting these back from the ADTRAN. And eventually the ADTRAN shuts down the communication, then it sends us another SYNAC. I don't know why, it just shut down the communication. We acknowledge, and then we say, you know what, we're done here. We're not going to talk to you anymore. It's been 9 seconds. We're going to shut down. So we've got all that going on. So what's a good communication look like? What do things look like up here? Well, in a good communication, when things don't seem to go so badly, our server is actually sending the request off to a Juniper device. And when we get a response back, we're getting the response back from the NetScreen. And if we go ahead and walk down through these different packets, we can see we're always sending to a Juniper, and we're always getting responses back from a NetScreen. So this is nice and consistent. So we're still dealing with the NetScreen that we saw in prior cases, but we're sending to a Juniper. We're receiving from the NetScreen, not the other way around. So what's going on here? Why the disconnect? Well, if we go ahead and find that bad stream again, and if we start to look at it, we noticed that we had these ICMP packets right before, and they were redirect packets. And we know we have a problem where we're taking a different path for some reason yet unknown. And if we actually go and pull these apart a little bit, we can see that the redirect is coming from the Juniper device. And it looks like this device's IP address is 1.1. And it's telling us that we should be using a gateway of 0.2. Excuse me, the Juniper is 0.1, and it's telling us we should be using a 0.2. So we don't really know who 0.2 is. But the very next packet after this, and this is 440 milliseconds after we get that redirect that comes in, we go ahead and we start sending communication out through that NetScreen. So we can go out on a limb and we can say, you know what, 0.2 is probably the NetScreen. So is an ICMP redirect responsible for this? Well, if it is, why when we go back up to the top, don't we see the same behavior? The key to this is the delta time here. This is one of the reasons I love having the delta column. This redirect came in 15,000 seconds, excuse me, 1,500 seconds before we sent this SYNAC. One of the things we learned through this experience was that depending on your operating system, ICMP redirects only persist for a fixed amount of time. On the Windows operating system, Server 2008, I don't know beyond that, but for Server 2008, it looks like the redirects last for about 60 seconds. Different devices, different operating systems, the time is definitely going to vary depending on what that vendor chose to implement. So based on this redirect lasting 60 seconds, it didn't affect this particular communication because it didn't happen within the time window. But when we come back down here, this communication and this communication here were actually impacted because they happened less than 60 seconds from when this redirect came in. So why were we getting this redirect in the first place? Well, it turns out that the user had some traffic, some intermittent traffic on their network, that the router was configured to take a different path. And when this traffic came across, the Juniper tried to very politely move the traffic over to the better path as far as it was concerned, and it actually moved all the server's communication over to that path. And when that happened, that path was not set up to support the Projectwise traffic. And so the other traffic was nice and happy and did what it wanted, but Projectwise just kind of failed and floundered there. And 60 seconds later, when the redirect wore off, if there were no other communications of this specific type, the traffic would fail back to its main path and life would be good again. The user didn't disclose exactly what they did to clear up the issue, but they resolved it with some configuration changes. I believe they changed the way they were handling the redirects based on some information we got from them, and that cleared up the problem for them. So that actually brings us to the end of the presentation. I certainly hope you guys have enjoyed it. I'm certainly interested in any questions and comments you might have. We have my email address there, tim.poth@bentley.com. If you are interested in the capture files, if they have not been posted to the site, you can certainly ping me and I will be happy to pass those along to you. Thank you for watching and hope to see you at SharkFest 2013.